Like to request Kelly Snyder for his presentation on Vestiges of the Old Ways, test loops, PRVs, giant HPUs, and more. Can you please welcome him on the stage with a huge round of applause, ladies and gentlemen?
All right, I know we're a little bit behind schedule, but I do want to take a couple minutes here just to talk a little bit about the symposium itself. So Raj and I have had a lot of discussions about this, and it seems to be going pretty well. But I keep telling Raj, we're not going to do this every year. But he keeps putting it up there. Anyway, we made a few changes from what was done a couple years ago. One thing we're doing is trying to strike a little bit more of a balance. I'm sure that flow dynamics could fill up 2 days just talking about all our ideas and what a great group of people we are and what we're capable of doing. But I think I think we all should recognize that the reason we're here in the banquet hall of the Mayfair Lagoon is because of our sponsors. And that's why we're letting them talk a little bit about their products here. So I know this is a little bit disjointed because we have so many different presenters and a lot of these presentations are a bit short, but that's the thinking behind this, is we really want to thank them for making this possible and for all of us to get together here, have our lunch, have a chance to talk about all the projects and everything that's going to come on. All right, I think that was everything I wanted to cover. We can go ahead and get started with my presentation. So, all right. So the background behind this is that imagine my surprise when Raj and I started our own company and I tell Raj, well, this is great. We can fix all the dumb stuff that we were forced to do at the previous jobs. I said, I'm telling you what I'm going to get rid of. I'm going to get rid of this, I'm going to get rid of that, and I'm going to fix this other thing. And Raj says, hold on. We can't fix any of that because the RFP specifically has a deliverable that says we'll include it in our design. And I say, Raj, this doesn't work for me. So how are we going to fix it? How are we going to get rid of these things? And he says, I can give you 30 minutes after lunch, and you can try to convince everybody. So, obviously, as Raj covered, we've been designing slurry pipelines for longer than I've been alive, and they've come a long way. I think a lot of the vendors can tell you just how far their products have come, and that allows the engineering to get farther and farther. And we can do a lot of things that weren't possible when I started in this business 25 or so years ago. So, this is going to be a talk a little bit about why we did things the way we did before and also how we can move forward. So we're going to start with the mostly useless stuff. I added mostly in there because I didn't want anyone to be offended that they paid a huge amount of money for something that was completely useless. So we're going to start, basically there are two big offenders here. The first one is test loops. So as Raj alluded to in his coal pipeline presentation, they spent a huge amount of money on the first coal pipeline to do a lot of studies at different diameters, different grind sizes, different everything. And so the first slurry pipelines, imagine the excitement of those guys if they could install a test loop right next to their pump station so they could test all the different stuff and do their studies and all of that. And that was great, but it seems to have gotten copied and pasted onto everything. So in my entire career, I've only used a test loop once, and the only thing I needed that for was for the sampling point. I've heard stories that maybe they get used a little bit during commissioning. So let me just run through the bullet points. So they're primarily just tools for doing a little bit of scientific study, and we've got the science down pretty well at this point. They only work if they're perfect. So I need a perfectly straight piece of pipe, and it needs to be exactly level. If it's not, then I can't use it because you're going to have a slightly different elevation, and it's going to make a problem with all of the differential pressure measurements. They're almost never used. The other problem is that they work fine during commissioning when they're brand new. But the whole idea here is that this pipe is supposed to match your pipeline exactly. And the only time it matches it exactly is on day one. Because no matter what you do, the only way this could work is if you ran the slurry through there. Do I really only have 8 minutes left? Okay, anyway. The only way this could possibly work is if you ran the slurry through there all the time, because that's the only way you're going to get that test loop to wear and corrode at the same rate as your pipeline. So what happens is people use this during commissioning and then they shut it down. They either drain it or, I guess somebody might dry it out and purge it and keep it in pristine condition, but either way it doesn't match your pipeline anymore. So it's a very limited value. And what we've found is that slurry pipelines are a lot more forgiving. Well, I shouldn't say that. We've come up with very specific specifications on slurries so that they are forgiving. We've figured out which aspects of the slurry you can relax on and which ones we have to be very strict about. And so what's happened is we aren't that concerned about off-spec slurry. We aren't so concerned that we routinely send product to the tailings pond, which I think was the original intention, is you would run it through here and you would say, oh, that's not going to make it through our pipeline. We're going to send that off and dispose of it or send it back to the grinding mill or something. And that really doesn't happen. And I think of all the slurries I've seen, the least likely slurry for that to even happen on would be iron ore, just because of the way it's mined. And when I joined PSI in 2000, there were already people saying we don't need these things. So I personally have never installed one of these on any of my jobs, ever. Now, that's not to say I've run every job that's come out of every slurry engineering company I ever worked with, so these do get installed. But you don't want these. They're expensive and they take up a lot of space. So please, I would rather not have my first test loop be at flow dynamics. Help me help you. Let's not do these. And then I think the next one's really something. I don't know where this one came from. The oxygen scavenger system. We used to study these so much because we would have these copper concentrate pipelines that were almost something that we didn't need to put a liner in. Liners are incredibly expensive. It changes your entire way you construct it, and you have to go back in and install it, and then it creates all kinds of other complications. Not to say I won't someday recommend we line a pipeline. But we went through this oxygen scavenger so much. And the idea is if you can pull the oxygen out, then you have a lower corrosion rate. But the problem is these chemicals are really expensive. We're talking about sodium sulfite, which is the main oxygen scavenger, and then cobalt sulfate you have to add to be a catalyst. Because this sodium sulfite does not scavenge the oxygen that rapidly, and all we're concerned about with the oxygen scavenger is maybe the first 5 or 10 kilometers of the pipeline. And the reason that's the case is because any corrosion that takes place is going to automatically scavenge the oxygen. That oxygen will not be in solution. And any iron ore is also going to tend to pull out oxygens because it still has a little bit, it's not fully oxidized in general. There's enough capacity for it to pull out a little bit more oxygen out of there. So the whole premise behind this was for a different type of material that didn't scavenge oxygen, and it was to add it to the slurry itself. Now, water, because it doesn't scavenge oxygen, could potentially have a slightly higher corrosion rate than the slurry. It's very unusual, and the effect's not going to be that large. But I think that must have been the case when somebody did some corrosion testing. And so the concept became to install this enormous thing, this giant tower full of sodium sulfite, a mix tank, a dosing pump, all of this, only for use on batch water and flush water. And it just doesn't make any sense. I mean, I suppose from a technical point of view, I can continue to copy and paste the same exact thing into people's projects, but it makes no sense. Okay, if you really want to go that way, then you need a second tower, mix tank, and dose pump so that I can add the cobalt sulfate, which will obviously be very expensive. You don't need as much of it, but it's more expensive than the sodium sulfite. So let's just run down the bullet points real quick here. You don't need it for iron ore, but the water, you could say you need it for, but there's always going to be enough residual material in that pipeline that you'll have some scavenging ability. The water batches aren't that common, so even if your corrosion rate were something incredible, like 5 times higher when it's on water, you don't run the water batches often enough for the total, the aggregate total of all those water batches to matter that much. You're only trying to protect the first few kilometers of pipeline, and it's not even going to work without the catalyst. So I guess it got cut off, but this is an expensive system, both because you have to buy all that stuff initially for the capital cost, but also because you're going to need to continually add this material, so it's an operating cost issue as well. So I want to share a quote that there is nothing so useless as doing efficiently that which should not be done at all. So now I understand, everybody wants one of these, but I made these slides up so that when we have meetings about your project, I'm just going to bring this slide. So I don't like these. So now we're going to move on to things that are a little bit less controversial. All right, so these are hydraulic accumulators. We need these to run our high-pressure slurry ball valves, essentially. So they don't use motors. They're not electric actuated. We use pressurized hydraulic fluid. So one side is high pressure, one side's low pressure, and that's what turns the valve. And the reason we do that is because you can get higher torques that way than trying to do it with an electric motor. And this is an issue because when the valves are sealed, there's a lot of torque required to move them out of that static condition, because you can have 2,000 psi on one side and almost no pressure on the other side, and to try to... So the old plug valves, we would have to inject a hydraulic fluid to lift them off their seat so that you could rotate them. These, we don't do that, which is great, but it means you need a very high torque. And in order to get that torque out of something like a motor, you'd need an enormous motor, and then you wouldn't need it after it had first rotated. So that's how these ball valves work. And these are just the hydraulic the hydraulic power side of it. It's got a motor here to run a pump, and then inside there you've got some hydraulic fluid that it then pressurizes, and that's a little bit bigger version of it. But as you can imagine, when you have a very big valve and it's trying to turn, it uses up that pressure very quickly, and so these motors can't quite keep up. So the idea is to have an accumulator there that it can accumulate some pressure, and it can provide the pressure to continue moving that. And so we generally would want an accumulator anyway, but it would not need to be a very big accumulator. And what we realize is you can also use that same accumulator in case of a power outage, so you at least can close or open a valve in an emergency shutdown situation. So this is how they started out. Not that huge. They're basically half of it's just the power unit I just showed you. And then these cylinders are where we kept the pressure. And this was just to run a couple of valves. In case there was a power failure and our pumps tripped, we wanted to be able to shut those valves off. So that's what those accumulators were for. And that's how we wrote the specification for the hydraulic power unit on these early jobs. It's just shut down the valves, but the problem is we didn't reevaluate that specification. And so as we added more valves, and as the valves got bigger, and as the valves got higher pressure, the power units got bigger and bigger and bigger. I mean that's not so bad, but that's basically the size of a living room. And now we're getting up to almost the size of a house here with these cars parked next to it. And on some of the more recent jobs, we have to have two hydraulic power units because they're just enormous accumulators, enormous valves, and all of this. And it's getting out of hand. So nobody in the past dealt with the hydraulic accumulators. The issue was never considered a process issue. We just wrote in there, you have to be able to stroke all the valves a couple times with no power. And nobody really looked at what we needed in an emergency shutdown situation. So these just gotten bigger and bigger and bigger. I think moving forward in the future, we're going to have to take a look at what we really need, because we don't need hydraulic accumulators for pig launchers. We don't need accumulators for a lot of changes at choke stations and things like that. In the case of a shutdown, you're just going to leave everything where it is. So that one I think isn't going to be as difficult to implement as the other two. But still, I wanted to let everyone know, because this is going to change the look of some stations. All right. So this is a little bit better news. These aren't useless things. These are things I think we can improve on that are fairly easy to do moving forward, but still are going to represent a change. When I first started, we were using flushed plunger pumps and piston pumps, and they had just come out with these piston diaphragm pumps that we're using today. So a piston pump or a flushed plunger pump has physical contact from the piston to the slurry. And so if something happened, if you closed a valve downstream, or if there was some kind of pressure problem, that pump could continue to run and overpressure the station piping or the pipeline. And so we had to have pressure protection, and that was this valve here. It's a pressure relief valve that would be set well above the pump discharge pressure to protect the station piping. But a few things, because you couldn't put a pressure relief valve on a piston rod. But what's happened is, now that we have piston diaphragm pumps, the piston is no longer in direct contact with the slurry. There's a hydraulic fluid in between there. And so the idea is we can take advantage of the hydraulic fluid and put the relief valve inside the pump to relieve the pressure inside the hydraulic fluid rather than outside, which causes a lot of issues. The main issue we're running into these days is that we are trying to operate the pump so close to the maximum pressure, so close to the pressure rating of the flanges, so close to the pressure rating of the entire station, that there isn't really enough extra pressure available to get that 20%, to get us away from nuisance bursts on these relief valves. So I think I haven't cleared this with all of the pump vendors. I probably should have, but I think our goal in the future is to try to rely more on the internal hydraulic relief valves and eliminate these external relief valves as much as possible. They're rarely used, and they create some other problems with the design, as I'm alluding to. One of the more recent jobs, we got rid of this, and we had very few options on how to install that if we wanted an external slurry relief valve, because there just wasn't enough extra pressure, especially once you consider the natural pulsations of pressure coming out of this pump. We were worried about nuisance bursts. So I think that covers all the bullet points. I had these bullet points here in case we have to come back to them at some future meeting. All right. So lime we use to control the pH of slurry. So as we get to high pHs, it does a couple of things. But the main one is that when you have a high pH, it limits corrosion rates. And it also has some beneficial effects on the slurry itself. But in order to do that, we need a cheap source of, essentially, to lower the pH, is this lime material. So lime starts out as calcium oxide. And that's this rock-like material here, sort of like a gravel size. But the issue with that is when you add water, it releases a lot of heat, and it also has some grit in it and some other things that may be undesirable. So there's a whole process. You turn this rock into what we call milk of lime, which is a lime slurry. Lime is not very soluble in water, so it's like a white slurry almost. If you take that milk of lime and you remove the water and you dry it back out, you get what we call hydrated lime, which goes in bags like that and can also be transported by truck and other ways. It's a lot less expensive to buy the lime itself. The hydrated lime is more of a finished chemical process, and just removing the water takes a lot of energy, especially since we're just trying to turn it back into milk of lime. So my preference, especially since these are big pipelines that use a lot of lime, is just to go ahead and install the slaking system so that we can handle the large lime rocks. The other problem with the powders is that if you get them wet, they tend to clump together and cause other issues of that sort. So one of the nice advantages of the pebble lime is that you can store them in very tall silos because it's more of a rock. If you wanted to store the other material, it would be a smaller silo for sure, and often you want to keep that inside too because the waters are a pretty significant problem. But it is possible to handle the hydrated lime, and I accept that some people may choose to do that, but I don't think the economics are there to justify that, especially since in most cases we're using a lot of this, and it's an operating cost issue. So just something to keep in mind. That's my position on this, but I know that there are some clients that have strong opinions on this, but I did want to take a minute here to talk about that. All right, so on these piston diaphragm pumps, obviously there are a lot of pulsation issues. So they're essentially what a piston diaphragm pump is, a couple of check valves. And then the check valve slams open and closed, and that's where you get your pressure from. You have various pistons, and they're all pushing these check valves, and the check valves are slamming open and shut. And so you get a lot of pulsation coming out of these pumps. And so we put these pulsation dampeners on there, and those help to minimize and smooth out the bumps. Well, the way these are typically designed is they ship without any nitrogen in them, so they can't actually do anything because there's no pressure. So if you imagine this red part here, when it's shipped from the factory, it's just pressed all the way up there and there's no nitrogen. We call that the pre-charge. So there's no nitrogen in there, and if you tried to use it as a pulsation dampener, it wouldn't do anything. This diaphragm in here would just be pushed to the top all the time. You can inject nitrogen in there and push it down, and the pressure of your pre-charge will determine what pressure range this dampener will actually work at. The main issue, though, is that we normally don't have any idea where this diaphragm is. Basically, is it at the top? Is it at the bottom? We don't have any idea. We don't have any way of checking the pre-charge easily. And think about this. This can be very high pressure here. So your pre-charge could be very high, and there's no pressure gauge on it. So it's not easy. So I've been to a few sites where I'm not even sure if there has been any nitrogen put into it, or if someone just forgot to add it. And obviously there's a lot of pulsation. So these are not very expensive in the grand scheme of things. And what we've started to do on some other projects is install multiple pulsation dampeners. 2, sometimes 3, to cover a better range of pressures. And at the same time, you can select your nitrogen precharges for each of them, and you can potentially adjust them based on where your system's operating. And if we add a pressure transmitter to the SCADA system, we do some other things like that, this is a fairly low-cost change, but I think you can expect to see, instead of one large pulsation dampener, we're probably going to end up with 2, or if you have a very wide flow rate range or pressure range, maybe 3. But in addition to that, we want to tie this back into SCADA so that the operators can see how these are operating to make sure they actually are working as pulsation dampeners. So that's another example of something I think we can do better moving forward. So expect to see that on upcoming designs. All right. Well, I don't know how late we are, but I'm definitely going to finish on time. All right. So a lot of people have this perception that I can just design a system in a few days and that I just copy paste the previous job and it's like super easy. But the truth is there's a lot of stuff that needs to get thought about, and the next 2 examples, I think, are places we're going to be spending a lot of time on in future designs. One of the biggest issues I have is how the pump station tanks are being designed. There's a question of how many tanks we need, because as an operator, I think it's pretty difficult to justify having more than 2 tanks, because I would normally operate the pump station at least. I would have all the flow going into one tank, and I would try to hold that tank's level at about half full. And that should do it. I have the other tank there as a backup, but I'm seeing some systems that are getting installed with 4, 6, 8 tanks, and there are some cases where that's made a lot of sense. We've had several multi-product pipelines where they had different grades of ore, or they had different types of ore, things like that, that they really wanted to keep separate. And so if you'd get one ore, you'd have to send it to tank A. If you got the other ore, it would to B. And you'd wait until you had a tank mostly full, and then you'd run a batch of that, and then you'd put a water batch in, and then you'd switch to another tank, and things like that. So there are certainly cases where you need a lot of tanks. And I think the intention behind putting in lots of giant tanks is that that gives you autonomy. But my question is so the agitators on these tanks use a lot of power. And my question is if all you have is one ore grade, are you really going to ever run all 4 tanks full? Because you're going to be paying for all that power. And yes, it's true that if you had all 4 tanks full and they shut down the mill, you could continue to pump for a long time. But I think this needs to get some serious analysis and serious consideration, and I'm not sure a lot of time is spent on this currently. We also generally send all the slurry to a splitter box up here, and part of the reason for that is when we have a lot of different products and we need to be able to switch between tanks. But if all you have is a couple of tanks, or even if you had 4 tanks, you don't necessarily need a splitter box. I can handle it all with valving through a manifold at the base of the tanks. And I do think there's a question behind that, whether we really want to stick with that elevated design, because as soon as you do that, you need quite a complicated support system, and you're running pipes vertically through all the supports, and it causes some design concerns for me. So I think that's worth talking about. And then also the position of the charge pumps. Charge pumps are designed to have very short suction runs, and you can get away with a lot on these because you have such high tanks. If the tank is full, you can afford to have your charge pump way off in the distance because you have all that extra pressure running behind it. But if you want to drain that tank, if you want to run it all the way to the bottom, which is generally something we like to be able to do, you want to have those pumps as close as possible. Here they put the pumps basically inside the tank area. I think there are a variety of ways we can handle it, but these are just topics that I think need to be developed and need to be talked through, because I don't think just copying and pasting previous jobs really does it. I don't think we have the perfect solution yet. And also, the way you combine the flows is an issue. I don't think anybody's come up with something that's perfect on that. So just keep in mind that the tank area at the pump station is very much something that we're still working on, still trying to find the ideal solution. And then also the choke station layout. See if I can finish in 10 seconds. We started with vertical choke loops for very specific reasons, and because we wanted pretty small choke steps, but it's also possible to put them on a horizontal, which might be more desirable in some cases. So this is something worth talking about. There are pluses and minuses to each. And then also, how large of a choke step can we accommodate? Because if we need to have small choke steps, the benefit of having small choke steps is that you waste less power. You can get closer to the perfect amount of dissipation. Larger choke steps mean usually you're going to have to be using up a little bit of extra pump power. But if there's a strong goal here to minimize the size of the choke station, we can potentially eliminate one or even two of the loops, and we can make it horizontal, and we can really come up with a more efficient design. So I guess I had to rush through that a little bit, but I'm happy to talk about any of those topics at a little bit more length at another time.